can solve, right, the games Go, chess, well, solve, compete in Go, chess, and shogi. Shogi, I don't know what it is. So I thought, in order to explain this, we should use a simpler game that we can actually analyze and all know. So, yes, alpha, tic-tac-toe. Or we could call it, what is it, noughts and crosses? That's what they call it, is that right? Yeah. There we go. So that's the British approach. Okay. So that's what we're going to use as our example. All right? So we have, come on, scroll. Can I not scroll? Okay, how do I get another? Okay, new page, fine. So we have a neural network. Coming into the neural network, we have what? State. What would be the state of a tic-tac-toe? Do we need any history? Do we need to know how we got here? No. All we have is a tic-tac-toe board, right? With some X's and some O's. That is input. Yes? Okay, now we're not going to actually input the lines, of course, but we just have to represent what's on each of the 9 spaces. And what's going to come out of our neural network is 2 pieces. One piece is what? Value. So the value is, from the point of view, let's say, of whoever's going to play, and I think X always starts first, right? So from the point of view of X, is X going to win or not? And in this particular example, I don't know what the answer is, but let's say V is 0, right? It's going to be a draw. And the policy is the other piece. We can represent the policy, if we'd like, as something like this, right? Visual's nice. So what are the possibilities? Right? How do we represent a policy?
What action you want to take?
Yeah. Yeah, but we're not going to be deterministic necessarily. It's going to be probabilistic, so we're going to have some probabilities for taking particular actions. And as far as the neural network is concerned, any action is fine. So what's the probability of putting an X here where there's already an X? Probably not absolutely 0, and probably at the beginning, pretty high. So this might be, I don't know, 0.1, 0.1, 0.1, 0.1, but maybe it's turned a little bit. It's not good to place on where stuff is existing, and so the remaining, it hasn't learned very well, has it? Maybe it thinks, let's see, we should have a point that this is a good place to play. Four, 5, 6, 7, 8, and we have 0.1 and 0.05 and 0.05. I don't know, right? This is just, it's the neural network as it happens to stand right now. Okay? So the neural network, we would hope over time would learn the rules of the game implicitly. And we kind of like to teach it, you shouldn't go at illegal spots, right? That'd be kind of a low bar, but one bar we'd want to have. So don't go where you're not allowed to play, right? And ideally, what we would like as its highest probability in this particular input. Where do we want it to play? In 9, because if we have any reasonable opponent and you don't play there, they'll go and play there. Now the good part is it's playing against itself, so if it's not smart enough to place an X here, maybe the O won't be smart enough to play an O here either. But the concept makes sense of the neural network, right? This is what we're training it how to play, basically. And how to play is you're given a state and you figure out what the probability of where to go is. And you do a good job of that. The value is something that we're using along the way in order to improve our policy. All right? And they'll both get better. Does this part make sense? Okay, so that's what we're learning. And the particulars about this neural network, I mean, hardly matter, right? We're going to do convolutional neural network and some other stuff, but we've already learned about that. There's nothing special here. All right, so now we need to see how to use this neural network in order to get better training examples. Right? Basically, in order to get some supervised input so that this can learn. In the case of tic-tac-toe, it's such a small game that we could probably just write down all the possibilities and by hand label them and say, this is how you should play. Right? These are the probabilities. But we're not going to do that. Right? We're going to go ahead and do this self-play. So let's say, and we're going to do a bunch of games, right, against itself. So let's say we're in the middle of a game. And it's the middle because the beginning's somewhat less interesting. So let's say this is our state. We have X, O, and X have gone. All right? And we have run this through our neural network. And our neural network has, so we feed this through our neural network. And our neural network has come out with some probabilities, right? In this case, let's say it's, I don't know, 0.1, 0.1, 0.2, because it's not totally stupid, 0.1, 0.1, and we have 0.1 there or something. Okay, so the total does need to add up to 1. Right. So what do we do now? We're going to use the Montecarlo tree search. Right, so we're part of our Montecarlo right now in the sense that we're doing a bunch of episodes. Right, we're going to do a bunch of episodes of playing a game. And here, we're going to actually do a bunch of episodes of playing from this particular starting point. So at every point in the game, we're going to do Montecarlo simulations to try and figure out what the best thing to do is at this particular spot. So at this particular spot, we've got the neural network, and it's telling us what to do. But we'd like to come up with something better than what the neural network has said for this particular state. And so we're going to run some Montecarlo simulations. So we're going to end up with some better policy. So for this particular state. So it's not really a general policy. It is a part of a policy, right? The policy for this state. And we don't know anything about any other states. But for this state, we're going to come up with a better policy, right? And once we have that better policy, we are going to, so kind of getting ahead of myself a little bit, so we're going to create a training example. So we're going to say the X is what? That is, what's our input to the neural network going to be? It's going to be a state. It's going to be this state, because this is the state we're interested in, right? This is the state we have before us. So this is going to be XO, OX. I'm sorry that that's not very readable. And the Y is going to be a pair, right? A pair of value and policy. The value, we're going to fill that in later. Okay? Basically, if we ended up winning, then it's going to be a 1. And if we end up losing, it's a -1. And if we end up 0, it's a draw. So for every move, every state in our game, we're going to wait till we get to the end of the game, see what happened, and then propagate back that value all the way back. So we'll hold on to this for the moment. But then the second thing, so is the probabilities. 0.1, 0.5, 0, 0, 0, 0, maybe if this is really good. It's going to be basically whatever this new policy is for this state. Okay? And we hope it'll be a better version than what we got from the neural network. And so the neural network will be trained to get a little closer towards this. Does that make sense? So if we have a game, how many training examples are we going to end up with per game? Okay, that's a good, so largest number. The largest number of moves.
Yeah, that's it.
How many is that? 9, right? We've got an empty board to begin with, and the last one is going to be all but one filled in, right? The last X remaining to go. Because we don't ever ask it, here's a completely filled in, what move should we make? Because there's no legal moves. So there's from 9 training examples we get out as a maximum for a given game, and the minimum is 5, I think, right? So we'll have between 5 and 10, 5 and 9 for every game. And we'll just generate a lot of games. Are we okay so far? So once we have training examples, we know how to train a neural network, right? So once we can generate these supervised, labeled training examples, we can go ahead back to our neural network and train it to do better and better and better and better. We just feed in more and more and more and more and more of this data, and our V's and our P's are going to start getting better and better. Agreed? Okay, so the only thing left is come up with a better policy, which we're going to do with this Montecarlo simulation. And the idea of the better policy is if we look ahead and see what happens after a couple moves, it'll be more accurate than if we just look now. So let's look at an example. We're in here, and we are now going to do a single Montecarlo simulation. All right? So we are going to simulate choosing an X. How should we determine which X to choose? Given that we know nothing about tic-tac-toe. Randomly based on what distribution? So we could do just randomly over legal moves. The problem, though, is we are not taking advantage of our neural network, which, although it starts out probably random, over time we'll be learning. So we're trying to better an okay prediction rather than better a completely random one. A completely random one could work. The problem, in tic-tac-toe, it's not so bad. You don't have that many states and that much branching. But you can imagine if you were working on chess, you don't think, what are all possible legal moves that I could make? And let me randomly pick one and look ahead for that. Instead, you're going to choose promising moves and look ahead from those. So we're using these numbers to pick a promising move. According to these numbers, what's a promising move? Yeah, go down the left, but what's 2, 3, 4, 5, 6, 7, 8. Yeah. And then the other ones are all equally promising. So we'll roll our dice, weighted dice, and we'll have twice the probability to pick this than we do these others. Let's not pick the lower left one just for fun right now. Let's say we pick the top right. What kind of a move is that? Illegal. Somewhere we have to have the rules of tic-tac-toe. Right? They have to be somewhere in our algorithm. They're not in the neural network, except maybe at the end they sort of are. Right? But explicitly, they have to be somewhere. And this is where they're going to be. Here, where we choose to play a move in a Montecarlo search, we're going to look and see, is it a legal move? And if it's not a legal move, we'll re-roll. Alternatively, we could rule out the illegal moves and rescale these probabilities. Right. Either one would be equivalent. Right. So we don't have to worry about the top right 4 cells. But along the left and bottom edge, we may have particular choices. So let's say we choose randomly this one. Okay? Half as likely as the best one, but just as likely as any of the others. We're going to label this. Well, we don't have a weight yet, so we're going to come back and label that edge a little bit later. And in our particular game, or our particular Montecarlo tree search, we're going to do 2 moves ahead and stop. Okay? What stops you from looking ahead a lot? Pardon me? Oh, so you get to the end. You get to a leaf node, like a terminal node is one possibility. What else would limit you? RAM, possibly. More likely, it's time, right? You want to do lots of Montecarlo searches, but if you run them also all deep and you have a huge branching factor at each time, right? Because here we're going to consider possible next moves, so on. So then it just take a long time. So we're going to limit ourselves, and for our case, we're going to limit it to 2. Because if we win all the way to 9, every time we'd go to the end result and see who won and lost, and it'd be really easy to figure out what the result is. So here we are, and now here's what we do. We say, what's the value of this? How do we find the value of this state? Who knows values? The neural net. It doesn't know very well, but it knows them okay, right? So we're going to get this from the neural net. And let's say the neural net says our value here is negative 0.5, which means, are we going to win or lose? Is it predicting? Yeah, we're going to lose. And if you were predicting it, what would you predict? That you're going to lose as well. So we're going to go back up here and we say, okay, we have a value. Our weight is negative 0.5. Okay? So this is our total value we've got. The 1 is how many times we have added value here. We basically want to know the average value for times we have traversed this. And so in order to keep the average value, we keep just the n in the total. But our average value is going to be at this point, q equals negative 0.5. And we'll go ahead and update that over time. Okay? We're going to keep going one more time, though. So we're going to say, OK, let's go. And we now have an O move to make. Give me a possible O move. Let's choose a stupid O move for a moment, right? Because it's going to get its share of those. So we choose. Oh, and how are we going to know what move to make? Is this policy going to be useful? No, because this policy is for this state. And we're in a different state, which is this state. So how do we get our policy? We go ahead and run it through the neural network. In fact, we already ran it through the neural network. We just pull out the P as well, right? So P
The same neural network gives the policy and
the same neural network gives the policy and the value. Yeah, and the advantage of that is you can imagine there's a lot of overlap between those, a lot of common features you'd want.
So when it gives you a value, this can be the value for the turn player or the player who just played?
We're going to say the player whose turn it is.
Wouldn't that value be higher?
Okay, we need to be consistent. So whatever we do, we're going to be consistent. Let's think about this. So whose turn it is. So therefore, we're going to call this positive 0.5. Okay. But this edge, it was still x's turn. So we're going to negate it to be negative 0.5. Yeah, you have to keep these things in mind. All right, so here we've got a policy. It tells us what to do for all these, right? What the probability is. And then we pick one from that random distribution. If we happen to pick O here, I can do a better job than this. X, O, O, X, and let's say we choose that. I didn't do a much better job, did I? Then, again, we want to know what's the value of this. And what's the value of this? Given that it's X's turn? Let's use our knowledge for a second. Can X win? Can X lose? Can X draw? Yeah. So it's not positive. I don't know. What's that?
Shouldn't the X still be in the middle one?
And there should be an X here, yes.
It's not that. X makes it stupid.
So X can, I don't see how X can win.
X can get the whole bottom.
X can get the bottom.
O goes next, right? No, O just, X goes next. Okay, X can win, fine. X can win, O can win, it's anyone's game. Right? Even though O gets to go next and could win in one move. But anyone's game. Oh, X, I'm getting confused. Yes, X gets to move next. So, okay. So, could lose if it was stupid. Could win if O is stupid. Or it could draw. Neural network says 0.1. Okay? So what do? Now we feed the 0.1 back up the notes here. We say n equals 1, w equals not 0.1, but negative 0.1, because we've got to negate it because it's with respect to O. Q equals negative 0.1. And then we feed it up again, up to here. So now n is equal to 2. W is equal to negative 0.4. And Q is equal to negative 0.2. So that says choosing this move is better than it was before. Right? It seems to be better than the first time we did it. The first time we got a more negative, and now we have a less negative. And as we go and roll the dice more times, we may get different values. Okay? In fact, let's say we roll the dice again. Okay? Back up a second. We're done here now. We're only going to look 2 steps ahead. Okay? We're now done with this Montecarlo simulation, this particular run of Montecarlo. Now we're going to do another roll of the dice to take another path through this tree of states. And we're going to go too deep. Okay? Does it make sense so far that we have now got, for this move, we know a Q value. For any of the moves, we don't know Q values yet. So we come back up. And we're going to, let's see how I can do this. We're going to change our color for our second run. So in our second run, we're still starting here again, because we're still trying to figure out what's the best place to move. And we looked ahead and said, well, if we move there, and if they move there, then we have a slight probability of winning. According to the neural network that says this. Right? They could be wrong, but it tells us. Let's say now we move. Well, first off, we have to decide how we're going to be choosing. Right? From what probability distribution we're going to use to choose a move. Before, we wanted to use the probability distribution that we got from the neural network. But now we have some new information. What new information do we have? We have the Q. So we have, if we play here, our current expectation of Q is it's going to be negative 0.2. And we also know that we have tried this with an n of 2. So from an exploitation point of view, do we want to choose this one? No, unless all the others turn out to be worse in the future, right? From an exploration, do we want to choose this one? Exploration says we haven't explored any of the others, so we want to choose the other ones. Does that concept make sense? Okay, because remember there was the Q and the U, and the Q is this Q value, and the U is this term that was inversely proportional to n plus 1. Okay, so that things that haven't been chosen are more likely to be chosen. So let's choose, I want to choose one where we actually end the game. Okay, so I'm going to choose this one. Even though, again, it's more likely we're going to choose something at the bottom left. Again, I'm adjusting the dice. So we have XO, OX, and I'm going to put an X here. Okay? And we look at the value, and the value is positive. Seems like if it was a reasonable neural network, it would think that this one and this one would be fairly similar because they seem pretty symmetric. But we're not forcing any symmetry. It would just have to learn that symmetry on its own. Okay? So we'll go ahead and say n equals 1, w equals negative 0.5, q equals negative 0.5. Okay. Does the idea of our second run through here make sense? Right? And now, what do? We choose an O move. How do we determine our O move? How do we know the probabilities? Neural network. Ask the neural network what's a good policy. If you're ever in this state, what would be a good thing to do? So we're going to ask the neural network. And in this case, the neural network has a great idea, right? It says with high probability, you should place there. And so we're going to follow that. And by follow it, I'm really just meaning we're rolling the dice, right, according to those probabilities. So we now end up with 0, 0, 0. Those aren't zeros, they're O's. Yeah? And at that point, the game's over, right? Who knows the game is over? How do we determine that? We have to know the rules. It has to be built in here. We have some code that knows what illegal moves are, and we have code that says when we're done with the game. And probably we want to know who won, right? So we have knowledge of the rules, and that tells us O won. So therefore, we're going to feed that back. We're not going to ask the neural network, what's the value of this? Because we're not going to ask the neural network the value of terminal states. We're going to use our knowledge of the rules to tell us the terminal states. So rules tell us O1 in this case. And so we're going to feed back. We're going to say n equals 1. We're going to say W equals so let me see again, make sure. So it's O's turn to play, and so therefore it's a 1 here, right? Q equals 1. And we feed up here, n equals 2, W equals, so a positive 1 here is a negative 1 there, so that's a negative 1.5. And Q is now equal negative 0.75, which kind of makes sense. In this one, it didn't look good for X, and this one was not good for X. Okay. At this point, we can now feed our training examples, save those away, because we know the final result. I totally take that back. Ignore what I just said. We're still trying to figure out a good policy here. Right? This is just one step in our game, and these are looking ahead. So this is pretending we did this and pretending we did this, and there's a lot of pretense. Eventually, we're going to continue the real game.
So this
Yeah.
trace
It's x here, so what should x do? And then we do the same thing for O. Once we finally figure out our new probability distribution, we're going to then choose a move for x. And now it's O's turn, and we're going to put that state at the top of the tree and go from there.
So is the final move being determined via the tree search, and that the output of the neural network is sort of a baseline for the tree search to give a final result?
The neural network is a baseline for the tree search. So it has a policy for the given state. The tree search is going to give us a more accurate policy for the given state. And we're going to use that more accurate policy to generate the move. And we're going to use a more accurate policy to use as a training example.
How do we determine, like, is it hyperparameters that determine how deep we go and how many times we do it? Or
The way alpha 0 works is it doesn't actually have a fixed depth. It goes as long as, I think, as long as stuff kind of looks interesting and it has CPU budget.
then
far as
how do
it
you
goes.
decide how many, like, branches to go down?
That was what I thought we were just talking about, is how many branches to go down.
Like, that's how deep you go.
Yes.
So how do you decide how many times to try going down?
Oh, again, probably has to do with your CPU time. That's something you could easily distribute, right? So you could just, I think they did 1,600 Monte Carlo simulations per move. If you wanted, you could distribute that, presumably, but the depth you can't distribute. That's a serial thing. Yeah.
So the value, that's 0.1 right there, so does that apply to just the O move? I don't understand why you're switching from X to O and then getting these values.
So it's X's turn now,
Yeah, so
right?
I thought it was always sort of only applies to one player throughout the tree search.
The tree search. So here, let me give you an example. It's X's move now. X is trying to figure out a good move. X looks and says, okay, if I move here, then what is O going to do? That's the what is O going to do here. So we have to evaluate that in terms of what might O do. What is the response counter response that can happen? Okay. But we're using all this just to figure out what's X's move. All right.
So, implicitly, like, are we assuming that the value of our opponent's state is like the negative?
Yes. Yes. So if we have a 0.5, which means we think we're likely to win, then our opponent has a negative 1.5.
So if it's like a non-zero sum game, we'd have to like take some alternate approach.
Yeah. Sure seems like it. All right, so we do this many times, and then we now have an idea of what the cues are for every one of our possible moves, or at least the moves that we explored. And roughly, we're using those cues to update our policy. So that our new policy says, basically look at the cues. What are the good values? Right? If this cue is higher than that cue, then the probability should be higher here. So hand-waving a lot of stuff there, but that's the idea. By looking ahead, we certainly here, right, got to a final state. We didn't have to use V, our current poor neural network, in order to figure out whether this is a good state or a bad state. The rules tell us whether it's a good state or a bad state. Here we are using the V. Okay. But imagine in our training examples, as you get to the end of the... So let me back up a second. Our V's are going to be better and better because our targets for our V's are always 100% accurate. Our policy targets are not 100% accurate. Right? Our policy targets don't really tell us exactly what to do. They just say, this is better than you were. Our V's tell us, at least given the player so far, this is the accurate value. Right? We know the way the thing plays, whether it wins or won or lost, this particular game.